So in this video, we're still in section 4.2, 4.3, and 4.4. We're trying to transition over to the meaning of the first and second derivatives and start talking about things called critical points and things called inflection points. So this is the eventual goal. But one thing that we're looking at the moment is different functions f of t. In this case, we're looking at the function 2 to the t. You can see that, maybe I should draw it in the right color, that the function f of t is in blue here in the graph above us. Okay, and we know just the pure formulas. We know how to take the derivative of 2 to the t, and we know that this is an exponential function. Okay, and because it's an exponential function whose base is equal to 2, then we know that the derivative of that exponential function is going to be the same exponential function with a compensation factor of the natural logarithm of 2. This is what we've shown in the past. And then we also know that the second derivative of this function, f of t, would be the derivative of the first derivative. Okay, so this is just purely the formulas. Logarithm of 2, while it's a fancy number, it is just a number, it is just a constant. So we bring that out in front of the derivative symbol. Okay, and then we have to take another derivative of 2 to the t, which would make a second logarithm of 2, and then we get the 2 to the t back again. Okay, so for example, if we're just doing the symbols, we could say that f prime at 1, 2 to the 1 is 2, would be 2 times the logarithm of 2, and f double prime at 1 would be 2 times the natural logarithm of 2 squared, right? So that's just purely the mathematics in taking the derivatives, okay, of a particularly an exponential function. What we want to do is to try to look at that in terms of the graphical values and the numerical values as shown above, okay? So what we're seeing here is when we computed the derivative at 1, we got 2 times the log of 2. So what it means to take the derivative of a function is we look at its tangent line, and we need to look at the slope of that line, and that comes out to be, the slope of that line is 1.39. Okay, so that is what f prime at 1 was supposed to be graphically, 1.39. Now let's check and make sure that 2 times the natural logarithm of 2, this is how my calculator does the natural logarithm, convert that to a number, let me make this a decimal, 1.39. So that's where this 1.39 comes from, okay? The question is, right, what does the f double prime mean? We have f double prime at 1, okay? We have that f double prime at 1 is equal to 2 times the natural logarithm of 2 squared. That is equal to a number. What does it mean, right, graphically? Well, if you're finding a derivative of a derivative, f double prime at 1 is the slope of the tangent line to f prime at a time t is equal to 1. So if we look at the 2 to the t times the logarithm of 2 graph, if we look at this right here, that is the graph shown in red. Okay, let's go to a time t is equal to 1 and find the tangent line to the derivative at t is equal to 1. What is the slope, excuse me, what is the slope of this line going to be? Right? And the slope of that line is evidently going to be 2 times the natural logarithm of 2 squared. Okay, so let's compute that number on our calculator so that we can know kind of 2 times the logarithm of 2 squared. And this is the number that hopefully we're going to see in the table of values in a second, that would be equal to 0.96. Okay? So let's look at the table of values and see if we can understand what's going on with these values. Okay. Now, as always, when we're looking at a function, we can create a table of values for it. If we want the velocity or the first derivative, we need to compute a rate of change of the function values, the column to the left. And if we want the acceleration, we need to compute the rate of change of the column to the left, which is the velocity in this case. So let's see if we could figure out what these numbers are going to be in these two blanks. Okay, we know that our function, okay, is equal to 2 to the t. Right? And if we want to compute this box right here, okay, what we're trying to do is say that f prime at 1 is approximately equal to the function evaluated at 1.5, okay, which we can see according to our table of values is 2.8284 minus the function evaluated at 1 is 2, and then if we divide by, in this case, 0.5, we get 1.656 for that value. Okay. Now the question is what goes in the second box, the average rate of change to the average rate of change. Okay. Well, now that we know that 1.656 goes there, we can, and we have the rest of the values we need. The average rate of change to the average rate of change is 2.3431 minus 1.656. Okay, looking at these two values and subtracting them, and then we're going to divide by 0.5, which says that this number right here should be around 1.3742. Okay, so what we can say is that f prime at 1 is approximately 1.656, and we can say the second derivative at 1 is approximately 1.3742. Now this approximation might not be very good because we've got a time spacing of 0.5. Okay, so let's see what happens as we get better and better numbers. Okay, and keep in mind that what we're shooting for is to find that the first derivative at 1, we're shooting for 1.39 for the first derivative, and the second derivative, I think we're supposed to get 0.96. Okay, so those are the numbers that we're hoping to see in our tables of values coming up. Okay, so let's move to the next page here. Okay, okay, and I will let you take a moment to fill in the blanks. Okay, you try to fill in the blanks, and what we can see here from these two blanks is that we're taking h is equal to 0.1 in this column, and in this table h is equal to 0.01. Okay, now remember what numbers we're shooting for. F prime at 1 is supposed to be equal to 1.39, which was 2 times the logarithm of 2, and we're looking for the second derivative at 1 was supposed to be 2 times the natural logarithm of 2 squared, which is 0.96. So hopefully that's what we're gonna hopefully that's what you would end up finding. So fill in those blanks there. Okay. I'll pause for just a second. All right, so let's take a look at the values. Okay. Right, what we can begin to see here is that as the time gets smaller, right, right here, the average rate of change went from 1.53 at 0.1, and then when we go to 0.01 for h, the average rate of change is getting close to 1.4, so it's getting closer to 1.39, the 2 times logarithm of 2. And the acceleration, right, this should be getting close to 0.96, so right here 0.1. And when you compute those values, it goes down to 0.97, which is getting closer to 0.96. Okay, so if we wanted to find this number right here for the acceleration exactly, right, we could compute the values more exactly. Control C. Excuse me. Control V. Now let me put 1 here. All right. Let me pause for a second and I'll fill in the table of values. All right, so if you've had a moment to try to fill in the values here in the table, excuse me, we can do that. Here you can see that I've got the 2 to the t function, and I've put in a time 1. We've got the function values at 1.01, 1.02, so we've got a small time spacing. We got all the positions, and we've got the velocity, the average rate of change. We did the difference in the position over the difference in time, and that gives us the 1.39 that we were looking for. We're supposed to get the velocity is the average rate of change, or the slope of the tangent line of the function, 1.39. And we're seeing the acceleration, which is the slope of the tangent line to the red graph, which is a smaller number than the slope of the tangent line to the function itself. The slope of the tangent line to the red graph, the derivative, is the second derivative. And we can see that we're supposed to get 0.96 there. So if we do the limit problem now, if we want to put 1.001 and 1.002 and 1.003, we can see that the numbers are getting to be these numbers right here. The derivative at 1 and the second derivative at 1 are getting closer to 1.39 and 0.96. All right, so that's our first hint at the exponential functions, and we can see that the thing about the exponential functions is that the acceleration and the velocity are no longer constant, and they are changing in a very special way, and we'll look at that in the next video.